to. And then you can work on how do I train a model robust enough that I get rid of the light box. But that's sort of your exploration beyond. So that's a lot of talking. You guys want to see a demo?
Yeah, let's do it. A lot of people excited in the chat.
Very cool. So let's do this. So I'm going to run, I have the group inference, the model server running, and then separately I'm going to run a script that will take the cameras and the joint positions from the robot and send those to the model and then get the next actions back. So if I run this and quickly screen share. Okay, so now we're running inference.
Look at that.
Let's see how it does.
Quick. It's good speed.
Come on. Oh, get it in there.
It's close.
My robot is especially jerky. This poor one has been doing, it's been hard at work every day for 4 months. So It's starting to look a little extra clunky, I would say. Let's give it a different one.
So if people are building this arm and they want to make it smoother, what is because you want it to be a little, right?
Yeah, it's sort of an interaction of the inference and this arm being a little jerky on its own, and there are techniques to overcome that that are a little beyond where the course is right now. Mm-hmm. But you'll see, so like this model, it isn't very good at choosing an empty hole, but if you run it again, it's pretty good at finding one.
There you go.
But anyway, this is one of our models you can experiment with. This one is trained with almost entirely simulation data. It was 75 sim episodes of teleop and 5 real. So I'll stop that one. So that's my jerky little robot.
You have a name for it?
I was trying to come up with one. I feel like it's a little endeared to me now with how much work it's done. Okay, so that's the task, and that's the autonomy we're looking for. Obviously, better success rate would be nice, but really the focus of the course isn't making a perfect policy. But you can see that's a pretty small number of demonstrations relatively, 70, 75, and then only 5 real. And we'll talk about what that mixture means and why we did that. But for now, I actually want to pass it over to Shayon, and he's going to talk about some teleop tips. So like, how do you get the data to do what we just, to train the model to do what we just did?
Yeah, thank you so much, Shane. That was needed. That was interesting. You know, it's important for us to understand why this course, why are we doing this, how do all these of our stack, how do they come together to form this whole end-to-end workflow? So I think this course is really amazing, just showing people how to use what we have. Okay, so I am going to share my screen in just a second now. Okay, yes. Awesome. Yeah, so I'm going to be talking a little bit about teleoperation, data collection, you know, how to get to a policy basically, you know, through our data. So, you know, we just saw the policy running inference live, you know, so we trained. So we collected data first, then we train. But how do we get to good data? What's the metric for good data? So before we even get to that, we need to understand calibration. You know, we calibrate the robot. Why do we calibrate the robot? So, you know, calibration is one of the very first steps that we go into before we even progress in this workflow. Because if you get it wrong here, a lot could go wrong in the end. You know, so to calibrate the SO101 arm, I just want to point out 2 things. I'm not going to calibrate it live, but I'm just going to point out 2 things that we need to take note of that people usually overlook or forget, basically. So there's a calibration pose, basically. And one of the things that most people forget is the gripper. So the gripper actually has to be open, you know, at this point for calibration. That's one thing. And the next thing is also the wires. So when you run through the full range of motion, sometimes the wires could get in the way. And we actually need the full range of motion for this calibration to be correct. You know, imagine the policy running inference and the robot isn't calibrated properly. You know, it's going to send actions and the robot is going to do something different because it wasn't calibrated properly. You know, so that's just the first step. So then I'm going to talk a little bit about teleoperation, our cameras, what's a good demonstration. So I'm going to run this live. I also have my setup too, you know. Um, so I have this setup with me. So Shane spoke about why we have two cameras, the risk camera and the environment camera. How once we pick up the file, the risk camera gets obscured. So the policy also has to depend on the environment camera. So at this point, during teleoperation, during data collection, you are the policy. You are the best example the policy could ever reference. You set the ceiling basically for how well the policy could perform. So we need to have good demonstrations. What's a good demonstration? So one of the first things we need to take note of for good demonstrations is our motion quality. So when we're trying to teleoperate, when we're trying to collect data, we don't want jerky motions. We don't want hesitations. We don't want pauses that just cause things to be distorted. Like if I'm trying to teleoperate and pick up this file, if I stop here for like 2 seconds and then I continue, the policy learns that pause. So we want it to be smooth motions, direct motions, straight to the point. We don't want excess parts that don't really mean anything in the demonstration. So, and I also want to just show us how to do this. Yeah, well, that looked easy, but I was looking at the robot. But when we are teleoperating, we don't look at the robot. We look at the cameras. So the cameras on my screen right now, the environment camera and the risk camera. We have to look at these because we have human eyes. And our eyes, we have depth perception. We have a lot of information. We can collect a lot of information with our eyes. But when it comes to webcams, cameras, there's not much the policy could do with that. So we have to train. We have to collect our data using these cameras because the policy would not have access to human eyes. So when it's running inference and it has visuals, it's gonna work with what it has. So if we collect data with information that the policy would never see, it's not gonna end well for us. So that's one of the key things we need to take note of. Another thing that we need to take note of is the episode length. I spoke a little bit about the episode length, which is, basically how long our episode is. The sequence. So we have like 3 sequences. You could break it into 3 subtasks. You first reach for the file, then you grasp the file, and then you place it in. This is gonna be a bad one. Not bad. And then you grasp it in. So those are 3 subtasks. We need to be direct, straight to the point. You reach for it, grasp it, and put it in. So those are just a couple of tips, and also data quantity. Yeah, I know Shane mentioned that we use about 70 sim and 5 real. It's important that our data is diverse. It's not redundant. You could have 200 demonstrations, 200 redundant demonstrations, same angle, same positions, everything's the same for 200 demonstrations. The policy doesn't really learn much from that. It's kind of what's the word now? Overfitted. Yes, thank you, Shane. Overfitted to that specific scenario. So we want to be diverse. Sometimes we can have the file in different positions. We could have a file start in the rack. We could just tweak a little bit, just play with it a little bit, So when we have that, we can have 70 demonstrations, 70 teleoperation demonstrations, and we have a good policy. It's just like learning how to catch. If you have a ball thrown at you at the same direction every single time, you're gonna be perfect. Okay, I can catch the ball here. But once it's diverse, comes from different angles, you have a more robust policy. You could adapt to new scenarios you haven't seen before because you have a wide range. Yeah, so that's what I wanted to talk about. So I'll hand it over to Shane for the next section.
Yeah. Thanks, Jen.
Yeah, great. Yeah, by the way, it was really. I could see you're going to be saving people a lot of time just with that advice.
Yeah.
Yeah, and that is a tricky one. You need to use the same inputs that the model is going to get. You can't cheat, right? And with your eyes and even just be able to move your head around, you're getting with parallax and like all this visual richness that our 640 by 480 webcam does not have. So that's part of the nuance of teleop. I want to give 2 bonus teleop tips just since you're all here for this task. Painfully figured out from doing this a lot of times, which is that it's a lot easier if you pick up by the cap. Two reasons why. If the gripper comes open a little bit, it'll catch on the lip and still stay there, won't fall. If you, it also gives you a little more ability to aim it. And then secondly, when you go to put it on, I think Shay might have mentioned this, but it's a lot harder to try to line it up and drop it because you don't have depth. So it's easier if you come down and try to find the hole and then let go of it. And if you noticed in the rollouts I did, it sort of tried to do that. It would like touch the rack, and if it missed, it would just still try to push down, and sometimes it would still succeed because it's trying to shove it into the hole, then let go. Otherwise, it's just like a bad basketball player. It's just like throwing at the hoop and it doesn't know. So there's a lot of nuance to teleop that you'll learn and through doing it yourself. But again, doing the course, you don't have to do 70 episodes if you don't want to. You can take our data sets, and as long as you build this workspace, which we've got a link in the chat for how to do that, you can transfer. So I think we'll move on to sim to real strategies. Yeah. So in this course, we cover a number of strategies. We mentioned earlier why it's hard, right? Simulation, as good as a simulation can be, the real world has differences that aren't always modeled there, but we have all these ways to make those things more aligned. And really, you can think of 2 main buckets of ideas for sim to real strategies. And this paper that we reference a lot in this course talks about this. It's called The Reality Gap in Robotics. And I think this idea has been presented on the stream before, but either reducing the gap or overcoming the gap. So do you overcome it by showing, say, like enough diversity that, like Shane was talking about, that, oh, it's already seen something in this distribution. Like the vials are way further to the right. It's already seen something like that because we showed that in sim and trained on that. Another idea is we try to align those 2 worlds more. And obviously we can't align the real world to sim, so we go the other way and try to make sim more like reality. Maybe we train a neural network on an actuator's behavior and we use that in sim or these kinds of things, right? So there's kind of 2 ideas, like overcome or reduce. So with that, that's kind of overview, and we just highlight a few strategies in this course. This is a huge topic, and sim to real is, at the moment of recording this, still very much a research space. Like if you give a task and a data set, like there isn't like, oh, that means you do X, Y, Z and it will transfer. It is a bit of an art and a bit of this clever application of these strategies, and people are trying to close this gap all the time. So we picked 4 to show you as examples. So Sharon, you want to talk about the first one?
Yeah. So thank you so much, Shane, for explaining the sim to real gap. It is a real thing, guys. The sim to real gap is real. So I'm just gonna share my screen again. So I have Isaac Sim up right now. So I ran the command in the course. I mean, you guys would have, this course is public now, so you could access this course. So I have Isaac Sim up now. The first thing I want to talk about, the sim to real gap. Shane has already spoken about the sim to real gap. So the gap is it's like a combination of multiple gaps. We have the physics gap, we have the sensing gap, we have the actuation gap. So we have multiple gaps. So how do we bridge that gap? How could we overcome or reduce the gap? So one of the techniques is domain randomization. I'm not sure if, some of us might be familiar with the domain randomization, but it's basically a sim to real technique where instead of trying to make simulation perfectly match how reality is, we could intentionally randomize some simulation parameters. We can intentionally randomize the lighting, the camera poses, the vial positions. We could randomize basically anything. You have control over the world in simulation, but we don't want to push too much. We want to randomize just enough. Like she said, it's kind of like an art. There's no one-to-one perfect way to do it. So I'm just gonna show us some of the domain randomization. So in this course, we randomize the lighting, we randomize the camera poses, we randomize some object positions. Sometimes the vial also starts in the rack. So this is Isaac Sim, our simulation platform. My physical SO 101 is actually connected to Isaac Sim right now. So as I am moving the robot in real, it's moving in simulation. This is something that once you try the course out, you'll also find out. So, uh, yeah, back to domain randomization. So once I randomize, we can see even the color of the robot changes, the lighting changes. Sometimes the vial starts in the rack. The positions of the vials are diverse. This comes back to the diversity I spoke about previously. When we have much diversity in the data, it's easy for the model, for the policy to adapt to multiple scenarios. So maybe I could even try completing the task in simulation. Let's see how it is when I only have access to the viewport. It's a lot harder than doing it in.
Oh, and sorry, Shane, make sure to change your cameras.
Yeah,
for that too.
Thank you. Also, we have cameras. Window, viewport 2. Thanks, Shane, for that. I almost forgot. So we have the cameras, the exact cameras we have in real. We try to replicate those in simulation. So like I showed you previously in my real setup, we have the environment camera and we have the gripper camera. So this is the exact same camera setup in simulation. Remember, in simulation we want to replicate the real as much as we can. So transferring that sim to real transfer gap, we want to try to reduce the gap or overcome that gap. So I'm gonna try to complete the task in simulation, and you can see how harder it is for me, even compared to doing it on the physical.
Backwards, it's even harder.
Yeah, plus the camera is backwards. Oh my goodness. Well, I'm not gonna try to complete the task, but yeah, that's just a little bit about domain randomization, how we have the physical robot connected to simulation also, and how we have the cameras in simulation. So Shane, you could take the next one.
Yeah, sure. So thanks for showing that. This is all part of the course, right? You can train. We start out with training in this environment, in the simulation environment, and the first model you deploy is trained only on simulation data. So the model has never seen, outside of the pre-training of GRUD, it hasn't seen the real world, and that's one of the models you'll see roll out. Okay, so next topic is co-training. So that was the policy that I showed earlier. And let me share this. So for all the data we've collected for this course, give me a second to do the sharing my screen thing. Okay, so for this course, we have all the data sets and models are on Hugging Face, which is a core part of how we did this workshop, right? Like, it's actually, on the small aside, this is a really fun part about Hugging Face, is being able to do a bunch of demonstrations here, share with my colleague in Europe, and then they maybe train a model on it or give me feedback on it, and then send it back to me and I evaluate it. And, because the time difference, we're working constantly, basically. It was really fun to be able to collaborate through the platform. So this is an example data set of sim demonstrations. And you can see we're trying to follow these principles that Shannon talked about, being smooth and deliberate. I wouldn't say that was the best pick. And this is my data, so I can be super critical of it. There's a better one. But then what we also did, so there's 75 of those, but then if you look at the very end of this data set, well, these look uncannily similar, but a little different. We've mixed in a little bit of real demonstrations. See if my internet can keep up, or maybe I have it in a different tab. There we go. So almost the same environment. Camera views are slightly different. If anybody picked that out, good eyes. I'll explain why that is in a second. But this is the similar demonstration, but with the real robot. So basically, the notion of co-training at a really high level is real data is really powerful. Real data has some of those aspects of the actuation, of the sensing gap and the actuation gap that we're missing. It has the camera noise, the distortion, the particular jerkiness of the robot, right? Those kinds of things are all embedded in that data, and you get some benefit out of mixing that in. Now, what's the perfect mixture? These are questions that are harder to answer. But this is a technique we found to be really successful. As an aside, when we were developing this course, we actually started with GRUD N 1.5, and we actually weren't able to get this task to complete, but with our simpler task of picking and placing into a tray, we had to use some real data for it to transfer. So it worked fine in Sim, but to get it to transfer, we needed this technique. And then when we moved to GarageBand 1.6, it was able to zero shot the tray task with Sim only. So we had to pick a harder task. That's a bit of behind the scenes of how we developed it. So that's the notion of co-training. And Hugging Face has tools for you to merge data sets. So you'll see like we would take this data set and merge it with a bit of real data and then train on that. Take this, merge it with some Cosmos data, train on that. So with that, why don't I hand it back to Shane to talk about Cosmos?
Yeah, thank you, Shane. So I'm going to talk a little bit about Cosmos and how we used it in this course. Like Shane mentioned, we had some sim demonstrations and we had real demonstrations, so we mixed them. We also have a data set with some sim demonstrations and some Cosmos augmentations. So for those of us who are not really familiar with Cosmos, so Cosmos is NVIDIA's World Foundation model for physical AI. You know, it's trained on massive amounts of video data. It's trained on many things. So it's learned how the physical world looks and behaves. So how we use it in this course is we've recorded demonstrations in simulation. You know, we want to augment these demos to look more realistic before we transfer them to the real world. But remember, we're trying to bridge that gap, the sim to real gap. You know, it's one of our biggest, let's say, issues in robotics now. Bridging that gap, because in simulation we have access to many things. We could do many things. We could train at scale. We could train 1,000 parallel environments. We could have a perfect policy in simulation. But how do we bring that into the real environment? So all these are techniques that we use to bridge that gap. So like I was saying, Cosmos. You know, we use Cosmos to augment that data. So, sorry, in plain terms, it's basically our output video in simulation. We give that to Cosmos with a text prompt, and Cosmos augments that and gives us a photorealistic image. So in the course, we also speak about this, what is Cosmos, how Cosmos works, how we use Cosmos in the course. So it's basically how we give it more bridging that visual gap. You know, there's multiple gaps. There's the actuator gap, the physics gap. So bridging that visual gap, you know, so simulation is good. It's really great, but we also want realistic visuals. You know, we want the policy to have seen some realistic images. You know, so when we train that policy, it could adapt to different scenarios. So yeah, we use Cosmos for that. So I think that's about it. Shane, am I missing anything about Cosmos? Maybe you could help me out here.
Yeah. So part of our strategy here, which we only had time to do a few iterations of this, but we knew when people did this workshop, they would potentially have different colored SO101s or different artifacts in their mat, or maybe they had tape on your robot or something. So like, how do we add more visual diversity to accommodate that? So they would transfer in more situations. And anecdotally, one of our team members said the Cosmos augmented policies work best on his robot, which had a different environment and a different color robot than ours. We had orange for most of ours, but as you see, we used domain randomization and sim to change that up. But this would allow you to do more. And you think about if you already have, again, after you go through the process of collecting demos, if you haven't already done teleoperation, I'd say your first 10 or 15 episodes are kind of fun. It's like a new remote control robot. This is awesome, especially if it's a new robot for you. Around episode 70, it's maybe less fun, I will say. And you'll understand how much time it can take. And so what if you could take data sets you already have? Maybe it's data from the real world. Maybe it was captured for an autonomous vehicle or in a factory situation that's hard to replicate. And this gives you the ability to augment those episodes or change them up with data you already have. So lots of ways to use Cosmos, but that was how we approached it for this. Shane, anything else on that, or should I jump into the last strategy?
I think that's about it. But maybe also just to mention, so Cosmos augments the visual stream. We have the same joint trajectory, same actions. So the robot performs the same actions. We just augment the visual stream. Yeah. So I think I just wanted to mention that. Thank you,
Yeah.
Shane.
Yeah, and just one last thought on that. As Shane mentioned earlier, the number of demonstrations isn't your only metric, right? How good are the demonstrations, and is there meaningful diversity in the demonstrations? So for us, we took the same demonstrations we had and augmented them with Cosmos and then mixed those in. And one of the things, come back to, and as we evolve this course, is we probably should have new demonstrations or swap those out so they're not replicated. But again, this just I hope this is bubbling up lots of questions for you, because every one of these parts, there's so many ways to explore and iterate on the possibilities of what would be the best. So hopefully you're getting that sense and maybe inspired to try this on your own. Okay, last strategy. You may be looking at the SO101, and let me grab one really quick. Okay, so if you're working with industrial robots, you would know this is not an industrial robot. It is, I love the SO101, but I mean, you can just see it has backlash, it has play that a real, let's say a typical industrial manipulator arm is going to have a lot less. So we know there's an actuation gap. You also think about how hard this motor, let's say, has to work when the robot is in this pose versus this pose. This becomes a large lever arm, and these are all the same motors, and they're daisy chained. So we sort of know there's some amount of actuation gap. And one of the things in this course is we've used group models that are using relative action policies. So GROOT can be trained at least 1.6 and I believe 1.7 can be trained with absolute or relative actions. So does it say, go more to the right, let's say, versus go to 2 degrees from the right? Just making up an example. So I think, and this is a bit of a theory I have, that the relative action policies behaved better, and I think they're another form of compensation. So how big is the gap? That's the point with this last strategy. So SAGE is a project, Symmetrical Actuation Gap Estimation, where you run a bunch of actions on a real robot on the simulated model of your robot, and you compare them. So this is my robot sitting right behind me. Somehow this didn't irritate my dog. I don't know how, but it ran like this for like 8 hours, just trying to explore its entire action space, basically, without hitting itself, and record all that data and run those same action sequences in Sim. And then GapoNet is taking that data and training a neural network. So think of it like, now that I understand how these two things diverge, how can I use AI to help converge them back together? So it's like a compensation layer. And so testing in Sim, this was really interesting. And I'll explain this maybe slightly confusing image. On the left, well, let's start on the right. On the right is 2 SO101s overlaid. You can kind of see there's like 2 grippers. So the one on the top is the Sim. So this is our perfect Sim world's robot executing this action sequence. The lower one is replaying real data back into Sim. This is like an Inception. I'm sure you're all going to hang with me, but so from real back to Sim. And there's a huge gap, right? Like, see, those grippers are not anywhere near the same place. And we think about that just in terms of our task. That's the difference between I'm ready to pick this file and I am not even close. So that's meaningful. Now, why are these two on the left so close together? Well, this has had a compensation layer applied with a tool called GapoNet. So if I go back, this is an estimate we did, the team who the GapoNet and SAGE team worked on. So they actually saw a 20 millimeter end effector positional error of the SO101 robot. And then with GapoNet applied, it got down to 6. So end effector being, in this case, the gripper. You can think of end effectors like the end of a robot. If you have a tool on the end of the robot, the tool end may be your end effector, right? For us, it's the gripper. And the error here is representing every one of those joints errors combined, right? Because they all link together serially. So that's a lot. I mean, 14 millimeters difference here. So I bet you're wondering, how much of an impact did this have on the performance of the group models if we brought this into the loop? And that is, unfortunately, at this moment, the cliffhanger is that we don't have that integrated. We've only done it in SIM. But this gives you a sense of there are ways you can measure these gaps, bring that data back into SIM, and use it to improve behavior. So that's a lot, but that is our workshop. Yeah, Edmar, do we want to take some questions?
Well, there's a bunch. But I would suggest, we have about 20 minutes, so I think we can probably talk a lot of these. We're going to go back in time a little bit because some of these questions came in a little earlier. And some of them, I guess, you might be able to answer super quickly. Some might take a little explanation. So I would say try to answer as concise as possible. We should be able to get through most of them. Okay, so here's one. So big thank you to Amelia, actually, for helping in the chat so much, as always. Can you share any pointers on Isaac Sim on the DGX Spark? I'm assuming. Can I try Sim to Real projects on it? Obviously, we've had so much interest on DGX Sparks, especially GTC when we had the Builder Claw tent, and lots of people asking when they can buy one and how they can use it, what can work on it. So, have you worked with this Spark at all, Shane or Sharon?
I haven't. I have a Thor right there. I don't have the Spark.
I have worked on the Spark just a little bit. But yeah, you could have Isaac Sim on the DGX Spark. You could install both Isaac Sim and Isaac Lab on the DGX Spark. I've used it a couple of times. I'm sure in the documentation, I'll probably send it in the link in the chat. The DGX Spark documentation, there's steps for installing Isaac Sim on the DGX Spark. Yeah.
Okay, great. Well, thank you for that. Great question from YouTube. Here's one coming in from LinkedIn from Aaron Franklin. Excited to dive into end-to-end learning workflows.